Hola, ba, test. Okay, it's working. Sorry, the microphone wasn't working. So, how to add processes during the simulation. So, you can see here in an example for what we did with the contact variables, which is what Thomas was asking me yesterday, which is something that produces this research. Which produces two text files. The shareable one just contains for each time step a set of value, for example, time, and this can be, I think, penetration, force, water pressure, and I think might be shear force and normal force. Honestly, don't remember. Doesn't matter. While the other one is much bigger, you can see here, and it provides for each time step the output at each node for, if I remember, position on X, position on Y, and force, contact forces, no, contact normal, contact force, and water pressure. And then you can use this for post-processing. In any case, the way to add these processes in pfem is in the JSON file, there is problem process list which contains all the processes created by Python or produced by Python, or add-on processes defined in Python that are applied during the simulation. So, for example, let's just use this much simpler simulation, which was just me trying to modify some parameters. You have the load process list, which in this case, for example, in a real simulation, you have the initial setting of the stress distribution based on top surface load, water pressure, and gravity. Here is just my custom function, which you will see later on. Then you have the problem process list, which does all the calculations needed, or the additional calculations needed during the simulation. So here, for example, the problem process list includes remeshing, it includes variable smoothing. This is, well, it controls the contact walls, the contact options, the non-local plasticity, and in this case, it also adds this specific process which export the contact variables. And then finally, you have the output process list, which is something that's done after the cycle. In this case, is export, restart, or export all the simulation data to restart the simulation whenever. In this case, while in this simplified model, I didn't have. Oh, we did have a restart. I forgot about this, but you can leave it empty. So, what does this contact variables does? It's defined in pfem application, which is, let me just scroll back. Applications, pfem applications, custom Python, custom processes. Nope, where is it? Python scripts, here it is, which defines all the additional processes, for example, some forces or cone penetration utility were the ones that were here by default. The one I've added was contact variables utilities, and then contact variables full. It's defined here. It takes an arbitrary number of parameters, and once the code is compiled, it's being a script. It's not compiled itself, but you can find it in the release folder, pfem application, and they're all here. So if you're not trying to do, or you're trying to just trying different things and you don't want to recompile everything every time, you can just modify them in the release folder, and that's or makes things easier. And then if you are happy with the results, you put them in the applications folder so that it gets saved by Git, because otherwise when you recompile, the bin folder for the release gets deleted. So how does this work? This process, you know where to find it because it's folder pfem application, name of the txt file, contact variables full, and then I have it here. I think I zoomed in. So it has, you define set of variables with a name and default value. If the text itself does not provide any uh, value for the parameters, it uses the default value. So for example, here model part name is where you want to extract it, or what part of the what mesh set you want to extract the data from. And here I don't want main domain, but I want solids auto one, which is the, let's say here, solids auto one, which is the geometry of the chalk itself. Output frequency is a custom defined variable, and the other one is just velocity, which is the insertion velocity in initial position. Then all these parts are converted from string to integer or string as constant or variable within, depending on the value, on the Python script. So self means it's a global variable for this script. And here, what does it do? It uses operating system, the Python library, gets current directory, creates these two files, and defines them, or the handle, as figure path and figure, or figure file and figure file complete. Then I just set velocity and time, t star. These are other parameters that don't matter, but you could add them as changeable variables, but in this specific case I didn't see a need to that. This is execute before output step. It's just well, stuff that was already there. Pore pressure anchor is one of the variables used for just obtaining the pore pressure on the object and in the entire domain. So what does this do? You have the model part name, which in this case is uh, solids auto one, so the entire domain. For each node, you'll get the nodes from model part, get nodes. For each node, you check if you have a degree of freedom for a specific variable. And if it has this degree of freedom, you get the value for the variable, otherwise you return 0. Then this is a bit of a faff. But yeah, create two empty vectors. Then I cycle again for all the nodes. I get the contact force, which is defined for every single node in the domain, even if for most nodes it will have a value of 0 because it's not in contact, and define a set of conditions. So I care that there is a contact force, otherwise I'm summing something that's 0. I'm getting the normal of the contact force, which means the how do you call it? Well, the orientation of the node. So if this is face, these are the nodes in this face. Let's say these curves here. This, in this case, this will be the normal, and it's just the orientation of the contact. So I get the normal, and I care if the sum of the normals is positive, which just means if the object has a normal, if the object is within, if the node is within a mesh, for example, here, let's say this node here does not have a normal because it does not its element does not have a contact surface defined. So for example, if you go back to GID here, geometry, edit, no, utilities, swap normals, line, select, you can see the orientation of all the normals of the faces, but inside the geometry itself you don't have normal. So in this case, what this condition is checking is if it's a boundary node. Then condition 3 is, it used to be if the solution step value variable is measured is exists basically, which meant water pressure. But in this specific case, I just changed it so that if the node belongs to a wall, which is rigid, then this condition is not satisfied. These were all stuff made for the anchors with Alessio. The tangent of the anchor is just obtained as the position of the anchor on X and Y. So if I define a starting position here and it searches downward, it finds the bottommost node, you know the uppermost node, so you can use this inclination to get the angle of the anchor, but it doesn't matter. These are just conditionally defined. You just consider that the node is within this position on X and Y. It applies these conditions and just says, okay, uh, for each of these nodes, get the elements, or for each of these nodes, create a list of nodes that are considered acceptable and add them if they respect all the conditions to this vector of nodes, which are the one defined above here. Then if you're trying to get the total pressure acting on, for example, the anchor, define instantiate the variable, cycle for all the elements, you get the node of each of the elements. If the node is part of the nodes that were defined as okay, you add the water pressure, otherwise you don't, and then you add the counter of the node plus 1, and so you have the average pressure acting on the anchor as total pressure by 5 divided by node counted, which is what this function was getting, pore pressure on the anchor. Then this one is executed after the output step, so then again this does the same thing. Then execute the final solution step. This is what I use to get all my outputs. So time is from get step time, which is defined somewhere. Get step time. Yeah, which takes the Kratos multiphysics.time process info and just returns it as a Python value or variable within Python. So that the model part, I've set a bunch of variables. I have contact variables, but this is just initiation setting values to 0. Then I cycle for each node in the domain. If the node has water pressure, set water pressure to this value, otherwise it's 0. Do the same with the contact force. And then I created this matrix that for each node it sets the x, y, the contact normal on x, contact normal on y, contact force on x, contact force on y, and water pressure, depending on whether the normal is, no, not the norm, the modulus of the force is positive or negative, and I add them to positive or negative based on the contact force, and well, if the node y is greater or smaller than 0, so just vertical position, then, and this was for, let's say, a tbar, so let's say file new, if this is the tbar and the axes are 0, 0, starting the reference initial position was 0, 0, depending whether the nodes are assigned to these two vectors, depending on their y position, so all the nodes above and all the nodes below, then I sort the nodes above and below that have a contact positive contact, so all the nodes that belong to the contact of the tbar. I sort them by position x, so from here from the left to right. Then I've counted the number of nodes. Then I obtain the water pressure for each pair of node. So let's just zoom here and just pretend these are two nodes on this portion here, two nodes here with their respective normals. I get the water pressure as the average, because 6 was the value here, which was the final variable. Then length is just the distance of the two nodes. We just Pythagoras, in this case here, which is the length of the element subtended by these two nodes, or the linear element. Here. Then I calculate the average of the normals. Then I calculate the water pressure converted to force by multiplying it by, so the water pressure is isotropic in the nodes. I multiply it by the length of the element and multiply it by the normal, so I have the force on x and y. Do this for all the negative pressure or all the nodes below, then do this for all the nodes above. It's probably a better way to do this, but whatever. Then I get force below and force above as the sum. This was just a function defined by Matteo that finds linear to exponential curve. So it starts at the very beginning, it starts linear and then becomes, no, it starts exponential thing. So that at the very beginning it's almost 0 and then becomes linear. But doesn't matter. This just calculates this function as the maximum of the two. So I have the time, the displacement of the pile, which is maximum of these functions, the f, x, and y total, which are just the sum of the forces, and ux and uy, which are the sum of the, the water pressure calculated here using the normal, the element length, and the node value. This just opens the file as append, so it doesn't delete what's previously there, writes the line and just closes the file. And this just is what creates the small file. The other part is the what I used for creating all the outputs, which is more occupies much more space. It's probably, I think it's more efficient for the calculation and less efficient for writing, but whatever. So I have figure path complete. I defined an initial time, um, output frequency. I just open the file. For each node I get water pressure, and then I just get this vector of data which contains time, ID, X, Y, normal X, normal Y, contact force X, contact force Y, water pressure, and just creates one line out of all these variables and writes it to the figure path, and then closes it and updates the time so that until the time is the difference is greater than the output frequency, this does no longer get executed, which in this file means output frequency 0.1, which means every 10 milliseconds of simulation time I get this output. This is all old stuff. This is just previous stuff that was already in the script that I didn't bother removing. Get different time. Get pore pressure is what Luis had said before, which is just get pore pressure at a given position, which just finds the closest nodes to the given position, checks if the nodes have an element between them, and calculates the value as it's a, let's say, a distance based averaging, and just returns. Get resistance is basically the same. These are all variables that were already there in the code, which I just modified because we didn't know the initial structure, but they're no longer used. Then, for example, I have this other function. So this is, I can check the time. Oh, 22 minutes in. So the Gaussian point utility, this is the same as the previous one, but instead of obtaining point or data from the element nodes, so we used, well, it's no longer there. Instead of using Gaussian DOF, it's get, what it uses is just the calculate on integration point instead of get solution DOF, and get on the calculation point what variable do I want. I know where the PT variable is contained. It's in the constitutive model application, so I define it where I want it to go. Obviously, I need to import it as well. And we get the position X, Y, Z of the element, or just the center of the element. So I just export the PT data, which is the stiffness, and write it to the file. And a bit more complicated is something if you want, or this is what I was trying to do. It doesn't work yet, but I'm gonna tell you about it anyway, which is this function to assign parameters. So the Python function itself is placed within the constitutive model application, custom processes, assign PT process, takes a bunch of initial parameters, and all it does really is when execute initialize, which is the very beginning, is called, it calls this other function which is called assign GP, which is Gaussian point parameter, according to the setting. And what this function does is, okay, this assign GP parameters. In order to call it, I need to add the C++ header file. here to the add custom processes to Python, which is part of the custom mode application custom Python. Uh, this is just basically copying the previous definition, uses some, I don't know, pbind thingy, and it just takes as a pointer to the parameter, a pointer to the process, model part and parameter, and executes this function. The function itself is composed by the header and the code. All the header does is just constructors for the function and the protected or internal variables, which are not public, which is pt, in this case the tensor strength, the gradient, since we're assigning pt based on a gradient just for test, and the initial position on y, and these are the same, just prints C out, then gets the process input, gets the element part, cycles for each element, const element, it gets the integration points of each element, in this case it's 1 since it's a triangular element, then it gets the constitutive law that belongs to the how do you call it, to the integration point, and then for each of these points calculates delta y as the initial reference height and the coordinate of the element, which is just obtained from rgeom.global coordinate, which is, yeah, then I get pt as reference pt plus gradient multiplied by delta y, and just sets this value. You need only to write it one time. I tried both because neither of them worked. And well, when I try to run this, it doesn't work, but if I try to output the constitutive law, it says element something for each element in the domain, and then it says constitutive law, which is a constitutive law and a series of variables, but this is where I stopped. But in any case, if you want to add a process, this is what you have to do. Just define C++ function, reference it to Python, create a Python, add the thing to Python as a function callable by Python. Then you define a Python function that does what you want, which is basically in this case just call this other function, and then again in the JSON call the Python that then calls this custom process to Python that then calls the compiled code here. And I think that's it.